Gas power cycles. This topic introduces the concept of gas power cycles as an essential part of modern power generation. The working fluid remains in the gas phase throughout the cycle, allowing the analysis to focus on changes in pressure, temperature, and volume. These cycles form the basis for understanding internal combustion engines and gas turbines. A thermodynamic approach is used to evaluate performance and efficiency. The discussion starts from ideal models before moving to real systems. Lesson Plan Thermodynamics 2. The course structure shows the relationship among various power and refrigeration cycles. Gas power cycles are placed as the foundation before discussing vapor and refrigeration cycles. This sequence helps build understanding step by step from basic concepts to more complex applications. Each chapter supports the others in explaining energy conversion. With this flow, energy system analysis becomes more systematic. Learning outcome. The learning outcomes emphasize the ability to analyze and evaluate various gas power cycles. Students are expected to apply simplifying assumptions to model real systems. Understanding reciprocating engines and gas turbines is an important part of these outcomes. Several ideal cycles, such as Otto, Diesel, Brayton, Stirling, and Ericsson, will be analyzed. Power cycles analysis. Most power-producing devices operate on cycles. In practice, the analysis of real cycles becomes complicated due to friction and other losses. To make analysis feasible, idealizations are introduced. This approach is not meant to perfectly replicate real systems, but to understand their basic behavior. From this, the theoretical performance limits of a system can be identified. Simplified, ideal thermodynamic cycle. By removing the complicated details from a real cycle, a simplified ideal cycle is obtained. All processes in this cycle are assumed to be internally reversible, without losses. The model still preserves the general shape of the original cycle. The goal is to simplify both mathematical and conceptual analysis. The results can then be used as a benchmark for real systems. Efficiency comparison of ideal cycles. Even though they are ideal, these cycles are not always reversible with their surroundings. Their efficiency is generally lower than the Carnot cycle at the same temperature limits. However, they still perform better than real cycles because internal losses are neglected. This comparison helps place ideal cycles within the performance spectrum. It shows the gap between theory and practice. Check your understanding number 1. This section serves to reinforce the concept that Carnot represents the upper limit of efficiency. By comparing the given statement, the role of a fully reversible cycle is emphasized again. The question helps ensure understanding of basic terminology. The focus is on distinguishing between ideal cycles and perfectly reversible cycles. From this, the concept of maximum efficiency becomes clearer. Analyzing thermodynamic processes with property diagrams. PV and TS diagrams are used as visual tools to analyze thermodynamic processes. The area enclosed by the curves represents the net work or heat transfer in a cycle. For ideal cycles, entropy changes only due to heat transfer. This makes the TS diagram especially useful for analysis. With this graphical approach, the relationships among processes become easier to understand. Carnot cycle. 4 reversible steps. The Carnot cycle consists of 4 well-defined reversible processes. 2 processes are isothermal, and the other 2 are isentropic. This combination results in a cycle with the maximum theoretical efficiency. Each step has an important physical meaning in energy conversion. This cycle serves as the reference standard for all other cycles. Characteristics of the Carnot cycle. The Carnot cycle can be applied to both closed systems and steady flow systems. Its efficiency depends only on the source temperature and the sink temperature. This relationship is expressed by the formula eta TH equals 1 minus TL/TH in plain text form. No other cycle can exceed this efficiency at the same temperature limits. Therefore, Carnot is used as the upper performance bound for all heat engines. Simplified air standard assumptions. The air standard approach assumes air as the working fluid circulating in a closed loop and behaving as an ideal gas. All processes are considered internally reversible, so losses can be neglected. The real combustion process is replaced by external heat addition. The exhaust process is replaced by heat rejection to the surroundings. With these assumptions, the analysis becomes much simpler and more structured. Answer B. The combustion process is replaced by external heat addition to simplify the analysis. Explanation of why other answers are wrong. A. The working fluid is a mixture of air and fuel acting as a real gas. Incorrect, because air standard analysis assumes the working fluid is air alone, treated as an ideal gas. C. All processes are considered externally irreversible to model real-life conditions. Incorrect, because air standard analysis assumes all processes are internally reversible to simplify calculations. D. Heat rejection is ignored to increase the calculated efficiency of the cycle. Incorrect, because heat rejection is considered as part of the cycle to return the working fluid to its initial state. Ignoring it would misrepresent the cycle. Reciprocating engine nomenclature. The piston motion is limited by two extreme positions, TDC and BDC. The cylinder volume changes periodically following this motion. The distance between TDC and BDC is called the engine stroke. These definitions are important to understand how volume changes during a cycle. From this, the basic geometry of a reciprocating engine can be analyzed quantitatively. Engine compression ratio and cylinder volumes. The displacement volume is defined as the volume change from TDC to BDC. The remaining volume at TDC is called the clearance volume. The compression ratio, R, is defined as Vmax over Vmin, or VBDC over VTDC in plain text form. This parameter strongly affects engine performance and efficiency. The higher the compression ratio, the greater the potential thermal efficiency. Understanding mean effective pressure. Mean effective pressure, or MEP, is a fictitious pressure representing the net work of the cycle. If this pressure acted over the entire power stroke, it would produce the same work as the actual cycle. Mathematically, MEP equals W net divided by Vmax minus Vmin in plain text form. This concept makes it easier to compare the performance of engines with different sizes. MEP provides a direct measure of how effectively an engine produces work. Actual four-stroke engine and ideal Otto cycle. This figure shows the difference between the actual gasoline engine cycle and the ideal Otto cycle. In the real engine, there are intake, compression, power, and exhaust strokes. In the ideal cycle, the processes are simplified into isentropic compression, constant volume heat addition, isentropic expansion, and constant volume heat rejection. This simplification removes mechanical details while keeping the thermodynamic essence. With this model, efficiency analysis becomes much easier. Nicholas Otto. The Otto cycle is named after Nicholas Otto, who developed the four-stroke engine in 1876. This engine became the basis for almost all modern gasoline engines. In one complete cycle, the piston performs 4 strokes over 2 crankshaft revolutions. This concept shows how the chemical energy of fuel is converted into mechanical work. Its ideal model is then used for thermodynamic analysis. Check your understanding number 3. This section tests the understanding of the relationship between piston strokes and crankshaft revolutions. The basic concept is that 4 strokes correspond to 2 revolutions. The question ensures understanding of the basic mechanism of a 4-stroke engine. By mastering this, the link between the ideal model and the real engine becomes clearer. It also helps connect thermodynamic analysis with engine mechanics. Efficient operation of 2-stroke engines. In a 2-stroke engine, all main processes are completed in only 2 piston movements. Compression and power occur almost simultaneously with intake and exhaust. The crankcase is used to help pressurize the air-fuel mixture into the cylinder. This design makes the engine simpler and lighter. However, there is a trade-off in efficiency and emissions. Advantages and limitations of 2-stroke engines. 2-stroke engines are generally less efficient than 4-stroke engines due to mixing of fresh charge with exhaust gases. Nevertheless, their construction is simpler and cheaper. Their high power-to-weight and power-to-volume ratios are their main advantages. This makes them suitable for lightweight applications such as motorcycles and lawnmowers. This design choice shows a trade-off between simplicity and efficiency. TS diagram of the ideal Otto cycle. This TS diagram shows the relationship between temperature and entropy in the ideal Otto cycle. Heat addition occurs from point 2 to 3, causing an increase in temperature and entropy. Heat rejection occurs from point 4 to 1, reducing the temperature. The lines labeled V equals constant indicates processes that occur at constant volume. With this diagram, the energy changes in each process can be understood visually. Key processes in the Otto cycle diagram. This diagram presents the main processes of the Otto cycle in PV coordinates. Compression and expansion occur isentropically, indicating no change in entropy. Heat addition takes place at constant volume from point 2 to 3, while heat rejection occurs at constant volume from point 4 to 1. The arrows on the diagram indicate the sequence of processes. This representation links the thermodynamic model to the piston motion in the cylinder. Answer D. Heat is added to the system at constant volume or constant pressure, raising the working fluid's temperature. Explanation of why other answers are wrong. A. Air-fuel mixture is expelled from the cylinder. Incorrect because the air-fuel mixture is expelled during the exhaust stroke, not the heat addition process. B. Heat is rejected from the system, lowering the working fluid's temperature. Incorrect because heat rejection, Q out, occurs in a different part of the cycle, not during heat addition. C. Heat is added to the system during the isentropic compression process. Incorrect because heat addition occurs during constant volume or pressure, not during isentropic compression, which involves no heat transfer. Compression ratio versus thermal efficiency in Otto cycle. This graph shows that the thermal efficiency of the Otto cycle increases as the compression ratio increases. Beyond a certain compression ratio, the efficiency increase becomes smaller and the curve flattens. The shaded area represents the typical compression ratio range for gasoline engines. This relationship explains why engine design is often limited by knocking. Thermodynamically, the compression ratio is a key parameter for improving efficiency. Impact of specific heat ratio on Otto cycle efficiency. This graph shows the effect of the specific heat ratio K on the efficiency of the Otto cycle. For the same compression ratio, a higher K value results in higher efficiency. This means that the thermophysical properties of the working fluid strongly influence cycle performance. Lighter gases generally have higher K values. Therefore, the choice of working fluid also plays a role in optimizing engine performance. Gasoline versus diesel engine.
This figure compares the ignition principles of gasoline and diesel engines. In a gasoline engine, the air-fuel mixture is ignited by a spark plug. In a diesel engine, fuel is injected into hot, compressed air and ignites automatically. This difference leads to different thermodynamic cycle characteristics. Ideally, gasoline engines are analyzed using the Otto cycle, while diesel engines use the diesel cycle.
PV and TS diagrams. Ideal diesel cycle. This figure shows the ideal diesel cycle in PV and TS coordinates. Heat addition occurs at constant pressure from point 2 to 3, unlike the Otto cycle, which uses constant volume heat addition. Compression and expansion processes remain isentropic. In the TS diagram, heat addition is indicated by an increase in entropy at constant pressure. This representation helps explain the fundamental difference between the Otto and diesel cycles. Check your understanding, number 5. This question emphasizes that in the diesel cycle, heat is added at constant pressure. This concept is the main feature that distinguishes the diesel cycle from the Otto cycle. By understanding this, the shapes of the PV and TS diagrams can be interpreted correctly. It also helps link the thermodynamic process to the operation of real diesel engines. This understanding is important before moving to efficiency analysis of the diesel cycle. Thermal efficiency of the diesel cycle. Compression and cutoff ratios. This graph shows how the efficiency of the diesel cycle is influenced by the compression ratio and the cutoff ratio. For a given K value, increasing the compression ratio generally increases efficiency. However, increasing the cutoff ratio too much reduces efficiency. This shows that the manner and duration of heat addition strongly affect cycle performance. Therefore, diesel engine design must consider both parameters simultaneously. PV diagram of the ideal dual cycle. The dual cycle is a combination of the characteristics of the Otto and diesel cycles. Heat addition occurs partly at constant volume and partly at constant pressure. This PV diagram shows the sequence of isentropic compression, mixed heat addition, and isentropic expansion. This model is closer to the behavior of real internal combustion engines. With this cycle, the trade-off between peak pressure and efficiency can be analyzed. A regenerator is a component that temporarily stores thermal energy from the working fluid. This heat is then returned to the fluid at another stage of the cycle without energy loss. In this way, the required heat input from external sources can be reduced. The result is an improvement in the overall thermal efficiency of the cycle. This concept is very important in Stirling, Ericsson, and regenerative Brayton cycles. Comparing Carnot, Stirling, and Ericsson cycles with TS and PV diagrams. This figure compares 3 important cycles using TS and PV diagrams. In the Carnot cycle, heat addition and rejection occur isothermally. In the Stirling and Ericsson cycles, a regeneration process is included and shown in a different color. This regeneration requires part of the thermal energy to be recovered within the system. This comparison shows how non-Carnot cycles can approach Carnot efficiency with the help of a regenerator. Answer B. Both the Stirling and Ericsson cycles include a regeneration process that allows energy recovery, enhancing efficiency compared to the Carnot cycle. Explanation of why other answers are wrong. A. Both the Stirling and Ericsson cycles operate without any heat rejection processes. Incorrect, because both cycles involve heat rejection, but they are enhanced by the regeneration process. C. The Carnot cycle operates at constant entropy throughout the entire cycle, unlike the Stirling and Ericsson cycles. Incorrect, because the Carnot cycle has entropy changes during heat addition and rejection, not constant entropy.
D. The Stirling and Ericsson cycles involve heat addition and rejection at constant volume, unlike the Carnot cycle's isothermal processes. Incorrect, because heat addition and rejection in the Ericsson cycle occur at constant pressure and temperature, and the Stirling cycle involves isothermal processes.
Stirling cycle with regenerator for enhanced efficiency. The Stirling cycle consists of four main processes involving isothermal expansion and compression and regeneration. The working fluid absorbs heat at high temperature and releases heat at low temperature. The regenerator stores heat during one part of the cycle and returns it during another part. With this mechanism, the required external heat input is reduced. As a result, the cycle efficiency can approach the Carnot efficiency. Steady flow Ericsson engine with regeneration for efficiency. The steady flow Ericsson engine uses isothermal compressors and turbines separated by a regenerator. Heat is added and rejected at constant temperature, similar to the Carnot cycle. The regenerator plays a crucial role in transferring internal heat between processes. With this design, the Ericsson cycle can also theoretically achieve Carnot efficiency. The difference lies in its practical implementation in steady flow systems.
Open cycle gas turbine engine. In an open cycle gas turbine engine, fresh air enters the compressor and experiences an increase in pressure and temperature. The compressed air then enters the combustion chamber and mixes with fuel. The hot combustion gases expand in the turbine and produce work. Part of the work drives the compressor, and the rest becomes net power output. The exhaust gases are then released to the surroundings, making the cycle an open cycle. Closed Brayton cycle with heat recovery for efficiency. In a closed Brayton cycle, the working fluid circulates in a closed loop and is not discharged to the surroundings. After compression, the fluid is heated in a heat exchanger before entering the turbine. After expansion, heat is rejected through another heat exchanger. With this configuration, the heat source can come from outside, such as a nuclear reactor or an external burner. This system allows better control of the working fluid conditions. Conceptually, it separates the combustion process from the thermodynamic cycle.
Check your understanding. Number 7. This question emphasizes the role of the heat exchanger in the closed Brayton cycle. The key idea is that heat is added to the compressed air in the heat exchanger before it enters the turbine. By understanding this, the energy flow in the cycle becomes clearer. This concept also reinforces the difference between open and closed cycles. The heat exchanger becomes a key component in separating the heat source from the working fluid. TS and PV diagrams, Brayton cycle. These TS and PV diagrams show the main processes of the Brayton cycle. Heat addition occurs at constant pressure, while compression and expansion take place isentropically. Heat rejection also occurs at constant pressure. This representation shows the relationship between net work and the enclosed area in the diagrams. With these diagrams, the effect of pressure ratio changes on cycle performance can be analyzed visually. Thermal efficiency of Brayton cycle versus pressure ratio. This graph shows that the thermal efficiency of the Brayton cycle increases as the pressure ratio increases. At higher pressure ratios, the temperature difference between heating and cooling processes becomes more effective for producing work. The shaded area represents the typical pressure ratio range used in real gas turbines. This relationship explains why compressor and turbine design is very important in gas turbine systems. Thermodynamically, the pressure ratio becomes a key parameter in optimizing the Brayton cycle. Net work output of Brayton cycle versus pressure ratio. This graph shows that the net work output of the Brayton cycle does not always increase with pressure ratio. Initially, increasing the pressure ratio increases the net work output. However, after reaching a certain value,
the net work starts to decrease if the pressure ratio keeps increasing. This means there is an optimum pressure ratio that maximizes power output. This concept is very important in the design of gas turbines for power generation or aircraft applications.
Backwork ratio in gas turbine systems. The backwork ratio indicates the fraction of turbine work that is used to drive the compressor. In gas turbines, a large portion of the turbine power is indeed consumed by the compression process. This ratio is defined as W compressor divided by W turbine in plain text form. A large backwork ratio shows that the system strongly depends on the efficiency of the compressor and turbine. This concept helps explain why improving component efficiency is so critical in gas turbines. Impact of pressure drops on gas turbine efficiency. This diagram shows that pressure drops occur during both heat addition and heat rejection processes. These pressure drops reduce the net work that can be produced by the cycle. As a result, the efficiency of real systems is always lower than that of the ideal model. This effect highlights the importance of good combustion chamber and heat exchanger design. In practice, pressure losses become one of the main performance limitations of gas turbines.
Answer B. The pressure drop that occurs during both heat addition and heat rejection processes. Explanation of why other answers are wrong. A. The absence of heat addition and rejection processes in real systems. Incorrect, because heat addition and rejection processes do occur in real systems. They are affected by inefficiencies, such as pressure drops. C. The elimination of compression and expansion processes in real systems. Incorrect, because compression and expansion processes are critical components of gas turbine systems and are present in both ideal and real systems. D. The inability to recover work from the turbine in practical applications. Incorrect, because work is recovered from the turbine in real systems, but inefficiencies like pressure drops affect overall performance.
Regenerative gas turbine cycle concept. In this configuration, heat from the exhaust gases is reused before being released to the surroundings. The compressed air is preheated by the exhaust gases through a regenerator. In this way, the fuel required to reach the turbine inlet temperature can be reduced. The result is an increase in the overall thermal efficiency of the system. This concept shows how internal energy recovery can improve cycle performance. Regeneration in Brayton cycle for enhanced efficiency. This diagram shows that part of the heat that would otherwise be rejected can be stored and reused. The regeneration process reduces the required heat input from combustion. The recovered heat is usually denoted as Q-regen in plain text form. With regeneration, the net work area in the diagram becomes larger. This explains why the Brayton cycle with regeneration is more efficient than the one without regeneration. Efficiency gains with regeneration in Brayton cycle. This graph shows that the efficiency of the cycle with regeneration is always higher than that without regeneration. The effect of regeneration becomes more significant at certain pressure ratios. The curves also show that the ratio between minimum and maximum temperatures affects how much benefit regeneration provides. This means regeneration is most effective when there is a sufficiently large temperature difference between the exhaust gases and the compressed air. In design, this condition must be considered for the regenerator to work optimally. Intercooling effects on compression work and efficiency. This figure shows that cooling between compression stages can reduce the compressor work. By lowering the fluid temperature before the next compression stage, the required work becomes smaller. The shaded area in the diagram indicates the work saved due to intercooling. This concept is very important in multi-stage compression systems. With smaller compressor work, the net work output of the cycle can increase. High-efficiency gas turbine cycle with intercooling, reheating, and regeneration.
This system combines three performance enhancement techniques at once: intercooling, reheating, and regeneration. The regenerator reuses exhaust heat to reduce fuel consumption. This combination results in higher net work output and higher efficiency. This configuration approaches the maximum performance limit that can be achieved by the Brayton cycle. Check your understanding number 9. This question reinforces that the regenerator functions to capture heat. This heat is then reused to preheat the compressed air. In this way, the overall cycle efficiency increases without increasing the maximum temperature. This concept is consistent with the main purpose of regeneration in thermodynamic cycles. This understanding is important to evaluate the benefit of each additional component in the system. Optimized gas turbine cycle with intercooling, reheating, and regeneration. This diagram shows how heat is added, rejected, and recovered in one integrated cycle. Intercooling reduces compressor work, reheating increases turbine work, and regeneration reduces the required external heat input. Overall, the net work output increases, and the thermal efficiency also rises. This system is an example of how several techniques can be combined to optimize performance. However, the system complexity and cost also increase. Multi-stage gas turbine cycle approaching Ericsson efficiency. This diagram shows that by increasing the number of compression and expansion stages, the Brayton cycle can approach the characteristics of the Ericsson cycle. Under ideal conditions, the processes become nearly isothermal. This increases efficiency because the average temperature difference during heat transfer becomes smaller. This concept is mostly theoretical because practical implementation is very complex. However, it provides an idea of the upper limit that multi-stage cycles can achieve. The nozzle in a jet engine functions to convert pressure and thermal energy into kinetic energy. High temperature and high pressure gases are accelerated as they pass through the nozzle. This acceleration produces thrust that pushes the aircraft forward. In principle, thrust is related to the change in momentum of the gas flow. Therefore, the nozzle is a key component in jet propulsion systems. Turbojet engine components and ideal cycle representation. This figure shows the main components of a turbojet engine, such as the diffuser, compressor, combustion chamber, turbine, and nozzle. The TS diagram shows how temperature and entropy change throughout the cycle. The turbine produces work to drive the compressor, while the remaining energy is used to produce thrust. Ideally, this cycle can be analyzed as a variation of the Brayton cycle. This representation links the physical components with the thermodynamic processes. Answer C. To generate work that powers the compressor, maintaining the engine cycle. Explanation of why other answers are wrong. A. To increase the velocity of the exhaust gases exiting the nozzle for propulsion. Incorrect, because increasing exhaust gas velocity is the role of the nozzle, not the turbine. B. To compress the incoming air before it enters the combustion chamber. Incorrect, because air compression is performed by the compressor, not the turbine. D. To add heat to the working fluid, raising its temperature for propulsion. Incorrect, because heat addition occurs in the combustion chamber, not in the turbine. Propulsive power, thrust and velocity in aviation performance. Propulsive power is defined as the product of thrust and aircraft velocity. P equals F times V in plain text form. This quantity shows how fast energy is being used to move the aircraft. The greater the thrust or the velocity, the greater the propulsive power. This concept helps link force analysis with energy analysis. In aircraft design, both thrust and velocity are equally important. This diagram shows how the energy from fuel is distributed into several forms. Part of the energy is used to produce propulsive power. Another part appears as excess kinetic energy and excess thermal energy in the exhaust gases. This shows that not all fuel energy is converted into useful work.
This analysis is important to understand where the main losses occur in propulsion systems. Turbofan engine, components, airflow, and thrust generation. A turbofan engine consists of a fan, low-pressure and high-pressure compressors, a combustion chamber, and turbines. Most of the incoming air flows through the bypass and produces thrust directly. The rest goes into the engine core to be burned and expanded through the turbine. This combination results in higher efficiency compared to a turbojet. Therefore, turbofans have become the standard for modern commercial aircraft. Check your understanding. Number 11. This question reinforces that high-temperature gases expand through the turbine. The energy from this process is used to drive the compressors. Without the turbine, the airflow cannot be maintained. This shows that the turbine is a key component in sustaining the cycle. This understanding is important before discussing larger engine configurations. Pratt & Whitney PW4084 turbofan engine, structure and thrust generation. This figure shows a real example of a large turbofan engine used in commercial aircraft. Air is compressed in several stages before being mixed with fuel and burned. The hot gases then expand through multiple turbine stages. In addition to thrust from the exhaust gases, most of the thrust comes from the fan bypass flow. This shows how modern turbofans emphasize propulsive efficiency. Turboprop engine, components, operation, and thrust generation. A turboprop engine uses a gas turbine to drive a propeller through a reduction gearbox. Most of the power is used to rotate the propeller, not to produce a high-speed jet. The main thrust comes from accelerating air with the propeller. The exhaust gases still provide a small contribution to the total thrust. This configuration is very efficient for short and medium-range flights. Ramjet engine, components, and high-speed operation. In a ramjet engine, air enters and is compressed by the ram effect due to high flight speed. Fuel is then injected and burned in the combustion chamber. Flame holders are used to stabilize the flame. The hot combustion gases expand and accelerate through the nozzle to produce thrust. This system cannot operate from rest and requires a high initial speed. Answer B. The forward motion of the aircraft compresses air as it enters the engine. Explanation of why other answers are wrong. A. A high-speed centrifugal compressor. Incorrect, because ramjet engines do not use mechanical compressors. Air compression is achieved through the aircraft's forward motion. C. Compression occurs solely due to the heat generated in the combustion chamber. Incorrect, because heat in the combustion chamber increases temperature, not pressure, and does not compress incoming air. D. A multi-stage axial compressor powered by the exhaust gases. Incorrect, because ramjets do not have axial compressors. Air compression relies on the aircraft's velocity. References. This section lists the main source of the figures and materials, namely the book Thermodynamics, an Engineering Approach by Chengel, Bowles, and Kanoglu. This reference is one of the standard textbooks in engineering thermodynamics. All main diagrams and concepts in this lecture are based on this source. With this reference, readers can explore more detailed explanations. It also ensures that the material used has a strong scientific foundation.